Hello everyone and welcome back to NL582, Modeling and Control of Electric Machine and Drives. In the last lecture we were talking about the modeling of synchronous generators, and we started developing what we call the equivalent circuit model of synchronous generators. Okay, and I want to keep emphasizing that I'm talking about the pair phase or a single phase equivalent circuit. It is because we know that we are talking about a machine that is its armature, which is the stator for synchronous machine. Just its winding is three-phase winding. That means it has three identical phases but separated by 120 degrees in space. Okay, so if the machine is just that symmetric, that means the winding are identical and the voltages, if it is a motor, so the voltage applied to it are also symmetrical. If it's just a generator, that means it will be symmetric. The voltage will be induced in this winding will be also symmetric. Symmetric means have the same magnitude and also 120 degree phase difference. Okay, so if this happens, that means you can just solve for one phase, and the two other phases you can just find out whatever information you want to find about them just by having 120 degree phase shift. So if we calculate, for example, the current for the first phase, phase A, then the current of phase B will be the same but 120 degree phase shifted, and phase C will be also the same but 120 degree phase shifted from B, and that's it. So we don't need just to solve for each phase alone as long as the machine is balanced, as it's the typical way of working. So that was the equivalent circuit we just revised. Okay, so the J-axis or axis we call the synchronous reactance, and the RA as the armature resistance. Everything is pair phase, so just that's for one phase with the three. Okay, and here is the induced voltage per phase. Okay, so I'm calling here A because I'm just targeting phase A, so everything here just for phase A, JXA, and RA and EA. Okay, and that is V terminal. Okay, so everything here just per phase, so that is what we call the single phase equivalent circuit. Okay, because I'm talking about a generator here, that means the current is going out of the machine like that. That's also a phase current. Okay, and if you wanna have the voltage equation for this, you will find that EA, and this dash means that's a vector, equal the terminal voltage plus RA pi A, and A is a vector or phasor polar, sorry, phasor form, plus JXS IA. Okay guys, all those that have in a dash on top of them, they are all in the polar form, and polar form means everything of those are just a magnitude and angle. Okay, and I'm keep emphasizing that is a phase quantity, and V terminal is a phase quantity, and RA and IA, sorry, are the phase quantity. Everything here is pair phase. Okay guys, so the whole point is for everything of those, so for example just EA, you will have it like an EA as a magnitude. Those mean the magnitude and angle theta of EA. Okay, that means it is in the what we called a polar form, if you remember when we just started recapping the AC circuits, because they are all AC quantities here because we're talking about an AC machine. So everything here should be dealt with a magnitude and angle. So if I asked you to find me IA, that means I want to find IA in the polar form as a magnitude and angle, not just the magnitude of IA, unless I stated it clearly. Find me the magnitude of IA. Okay guys, okay, so we also ended last time talking about what we call the Phasor diagrams, and something that's good for any kind of AC quantities you want to just picture in your mind. And we just said it will be different depending on the power factor you're talking about. So if it is a lagging power factor or unity power factor or leading power factor. Okay guys, so for the lagging power factor, we're just having this, we all the time assuming that the terminal voltage is our reference, that means it has an angle 0, And because it's a lagging power factor, there is IA going down like this, so the angle is negative, which angle theta, the angle between the terminal voltage and the armature current. They are all phases, don't forget this. IARA will have the same direction of IA, because RA is just a scalar form, doesn't have direction. And perpendicular to it, 90 degrees, so JXSIA, because this J means a 90-degree phase shift. And then if you add the three together, that will give you EA as a vector right here. And we said that this angle is delta, which we call the power angle or the load angle. Okay, guys? For unity power factor, just the same, but you know the idea is just the terminal voltage is here. That means IA has the same angle like terminal voltage because it's a unity power factor. And that means that is IARA. And JIAXS will be perpendicular to it, just like that. And the summation in a vector form for this give you EA. Okay, here the angle delta, and for this you know just theta equals 0 because we're talking about a unity power factor. That means IA and the terminal voltage having the same angle, the same direction. For the leading power factor, it was something like that. The terminal voltage is just right here, and now IA will be on top like that. The angle theta between the terminal voltage and the current is positive because it's a leading power factor. So IARA will have the same direction, and that is JXSIA, and the summation of them will be EA. And yet, that is the power angle or load angle delta. Okay, guys? That's pretty important. It helps you a lot just figure out what we mean or what are the relationship between those AC quantities. So understanding the phasor diagrams helps you a lot in this idea. Okay, guys? So the whole point we're trying to find out here is by modeling the machine using the per phase equivalent circuits, we can use this equivalent circuit to predict the performance of the machine with different operating conditions, and that's a very, very important thing to keep in mind. Okay, guys? So the whole point of this is if you have enough information, you can just use this equivalent circuit to represent the real machine. Okay? And it can give you a very, very accurate information about the performance of this machine. So you can find the current that can move its wind and find the different powers in the machine and the torque of the machine, whatever it is. Just like we did before with the DC machine, and you already did this with your hand, hopefully, and with the tutorial and the assignments and all that stuff. So actually you can do this, but you cannot do this unless everything in this circuit is known for the unique machine. Okay, so the terminal voltage is just basically a voltage at the terminal that can be measured directly using a voltmeter for a real machine. Okay, guys? But the other stuff, so the induced voltage, okay, is something cannot be measured, but you can find it because you know EA equals K phi omega, so you can find the relationship for it between it and the flux. If you remember on the DC with these tables between the field current and the induced voltage, so we can find a clue to find EA. Okay, so it is something also unique for this kind of a machine. Also RA and XS, the armature resistance and the synchronous reactance. Okay, so those need to be unique, so those need to be measured or estimated or whatever it is for each kind of or for each individual machine. Okay, guys? How to do this? Either the manufacturer of the machine does this for you and give it to you on the data sheet or the catalog, otherwise you have to do it in the lab. So if it's not given, you have to do what we call experimental tests on this machine. So you take the machine to the lab and perform these tests just to find out these. That's what we call the equivalent circuit parameters. So this, if I ask you what to do if you want to find the equivalent circuit parameters, those equivalent circuit parameters here are A, the armature resistance per phase, and XS, the synchronous reactance also per phase. Okay, so that is the per phase ones. And because again the three phases are identical, those resistances for all phases will be equal. So RA for phase A will equal R armature for phase B will equal the R armature for phase C, and it also will be XS the same thing. So the XS for phase A will equal XS for phase B and equal XS for phase C. Okay, so you just find it for one phase and should be there just identical for all the phases. Okay guys, and those are both RA and XS are unique, so those equivalent circuit parameters should be unique for each machine. Okay guys, so that's something you do it for the machine and you carry it forward and just use it with the equivalent circuit to find what you need to find about the performance of this machine. Okay guys, and that's why this equivalent circuit should be unique for each machine. So how to do this? Like I said, through what we call the synchronous machine testing. So we need to perform some laboratory tests to find those parameters of the RA and the XS. Okay guys, so I'll start by finding RA. How to find RA, the armature resistance? To do this, we can perform our first test here. We call it DC test. Okay guys, so how we just do this, we follow a definite steps. Okay, just bear with me. So number one, to do the DC test to find RA, as first, do not apply an external torque to rotate the rotor. Okay, that means keeping the machine at standstill. Okay, that means omega m, the speed, equals 0. That means you're keeping this equals 0. Why? I'll just say now, but that is the first step. So you keep the machine at standstill, to keep it stationary. We do not want to rotate the machine. You know that because we're talking about a generator. So the generator, you apply an external torque to force the rotor to rotate. Yeah? So no, for this test, we keep the machine without rotation. Okay? That is the first step. The second step, apply a DC voltage, and that's why we call it DC test. Okay? To any phase of the armature, which is the stator here, winding. So you just pick a phase of them and just apply a suitable amount of DC voltage on it. Okay, again, any phase, because they are supposed to be all identical, so it doesn't matter. Okay, so you apply some DC voltage over this. Number 3, measure the applied DC voltage and the DC current passing to the phase winding. Okay, so you measure both the DC voltage you already applied and the current will go from this source to the phase, and simply divide VDC, the DC voltage, by IDC, this DC current moving, to give RA. Okay, that's simple. So we are just trying to mimic the same thing you use, where just an easy ohm meter using to just measure any kind of resistance. So the ohm meter does this for you. It applies the voltage from its own battery, which is DC obviously, and measure the voltage and current, divide them together, and give you this resistance you want. But while you're talking about a big machine, so it will not be that accurate to use a regular ohm meter. Okay, but rather we can use this test. Instead, we apply a good amount of voltage DC, so it should be high enough to give you accurate results, to this kind of thing. The whole point is we forcing the machine to keep, so we do not rotate the machine, the speed is 0, and we use DC voltage. Why both of those? To understand this, let's go back to the equivalent circuit. That's JXS, and that is RA. And that is, I'm sorry, so we don't have brushes here. So that is the EMF, okay? That is EA, and that is the terminal voltage, yeah? For here, we are applying a DC voltage from outside. That thing we applied here, and that is VDC. Okay, guys? And the current moving here is IDC. Okay? So, number one, being at standstill, omega E equals 0. What does this will do for you? Okay? So, the speed is 0, and if you remember, EA equals K phi omega M. Okay? So, having a 0 speed means you are having a 0 induced voltage. So, this is now a short circuit. So, that's what they do. So, if the speed is 0, and that's what we need, we don't have an induced voltage inside the machine. Besides, using a DC voltage, not an AC voltage, that means the frequency equals 0, because obviously the frequency is 0 with the DC voltage. This will force XS to equal 0. So you don't have XS also. So XS is also short circuit like that. Because if you remember, XS equals 2 pi FLS. With having a 0 frequency means the reactance equals 0 here. So you don't have anything in this circuit right now except for RA. So you just have a voltage applied to this resistance. So it's an obvious Ohm's law. Okay, guys? So that's why we use the machine at standstill, and we use the machine with DC voltage, because we need to get rid of everything in the circuit except for RA, so we can measure RA alone. Okay, guys? So RA here, DC equals VDC divided by IDC. Okay? But this should be good enough, but still if we take more accuracy in our work here, so we need to make sure we have taken care of what we call the skin effect factor. Okay? Because if you're having the same wire and you having a DC current moving in it, so if you have a wire here, that is a wire, the DC current will move in entire cross-section area of wire. That's how it works. But if you have the same wire, but you have an AC current moving in it, the current tends to move in just the outer surface of this conductor. That means it works in an effective cross-sectional area less than the one occupied by the DC current, which just occupies the whole cross-section area of the wire. That means if you're talking about the same wire, if a DC current moves through it, it will face less resistance compared if an AC current moves through it. That's how this works, okay? That means the DC resistance we have measured here by a DC voltage applied and a DC current moving, it will not be the same resistance with the typical machine where that's AC current moving in. It's a synchronous machine, guys. That means what's moved actually in it is an AC current, not DC current. And we try to have those parameters, RA and XS, are close as possible to the real-time conditions of the machine, or the real-world condition of them. So we need to find how to correct this, okay? So we correct this by just applying a factor, comes by experience of the designers. So RA will equal a skin effect factor, which just from 1.15 to 1.25, something like that, multiplied by the DC value, like this. So this is RA DC that you come from DC test, and this what we call the skin effect factor. So the real RA is just a little bit higher than the one you've just measured by the DC test, okay? So if there's something in a problem in an exam or assignment or something, I will give you what skin effect factor I need. I will not just leave you with the range like this, okay? If it's not given, you just neglect it. That means it's not that necessary to include it at all. So just directly use the RA DC. It should be fine enough. Okay, guys? but in the real world you should incorporate the skin effect factor, and which is directly its exact number. It's something comes from the experience of the manufacturers. Okay guys, okay, so that was the first test, and now you have RA. Okay, but what about XS? We need to find XS now. So find XS, the synchronous reactance. Now we need two tests, cannot be performed with just one test. The first one, we call it the open circuit test, and the other one we call it the short circuit test. So two tests to find the synchronous reactance XS. Okay guys, we will take them one by one. So that is the second test here after the DC test, the open circuit test. Okay, so again it have certain steps we will carry out to perform this test. Okay, so the first one is open circuit the armature three-phase terminals. So that's why it's called an open circuit test, because we are leaving the terminals, the three-phase terminals of the armature open, not connecting them to a load. So they are just open circuit. That means there is no current moving in the armature circuit at all. Okay guys? Step number 2, drive the rotor using an external mechanical input until it reaches synchronous speed. And you know how to calculate synchronous speed, and AC equals 120 F over P. The number of poles is something you find from the manufacturer catalog. You know what's how many numbers in your machine, so you know this in advance. And for the frequencies, it just depends. So here in North America, it's 60 Hertz. In most other places in the world, it's 50 Hertz, okay? So you should know what the synchronous speed to expect. And why we want the machine to work at the synchronous speed? Because as we said, we are trying to have the machine in these tests work at the same condition that should be working in its real-time applications, okay? And the machine, the generator, the synchronous generator is driven all the time at its synchronous speed. So that's the speed that you should be examining the machine at. Okay guys, so now we drive the machine to work and drive the rotor with an external mechanical input, because that is how the generator works, guys. We just attach the rotor of our generator to a mechanical source to rotate it, to give it an input mechanical energy, and that is being converted into electrical energy through the generator. Okay guys, so the machine in real-time application or real-life applications, like you're talking about a power system, so it is in a power plant or generation unit or something, so it is connected to a mechanical source coming through the turbine. So if you have a turbine connected to the shaft, and the turbine is being operated or just rotated using some sort of a mechanical energy, a steam pushing through it, gas turbine, hydropower, wind turbine, whatever it is, okay? But because we're talking here about just a lab setting, so we have just our machine into the lab, so we'll be connecting the shaft to the same shaft with a motor. So we were just using a motor to rotate our rotor. Why? Because the motor just can be controlled easily. You can control the speed that's coming from it, so you can reach the speed you want and keep it like that. It will be much easier, and it also will be much easier to set up in the lab rather than having a whole mechanical turbine system. It doesn't make sense, okay? But to keep in mind that just a laboratory test, you cannot do this in real life and just give an electric motor to rotate an electric generator like you sometimes see on YouTube, because that would be very stupid to do. It's just, you cannot do this because the electric motor is taking electric energy to convert it to mechanical energy, and now you're getting this mechanical energy as input to the generator to convert it back to electric energy. So it did nothing but losing the losses in both the machines. So you actually keep losing. You do not do anything profitable here, okay? But for a lab setting, to just do these labs, we use a motor as our mechanical source to rotate the generator here. Okay guys, Yeah, I was just worth mentioning this because I keep seeing this dumb idea on YouTube all the time. It's just some guys having a motor connected to a generator and saying that's endless energy. It's nothing but crap. Okay. So step number 3 is slowly increase the field current IF and measure the terminal armature voltage. Plot them together. It's called the open circuit characteristics. Okay, guys? So, is it like this? You open circuit the machine, so let's go back to our equivalent circuit here. That is the induced voltage inside the machine, that is our A, and that is JXS, and that is our V terminal. But here we are keeping these terminals open, so we call this V terminal open circuit, OC, okay? You did nothing here but adding a voltmeter to measure the voltage here. But you do not connect it to any kind of a load or something, yeah? And you have the field circuit like this here, so that is our F, and that is the DC voltage of the excitation for the field winding, yeah? But now it is a controlled voltage source, so you can just control this DC voltage. And that means the current I field going here is changing with a change in this voltage, and you add an ammeter here to measure this current. Okay, guys? By keeping this open circuit here, that means there is no current moving through here, because that's an open circuit. So that means there is no voltage drop over RA or XS. So the terminal voltage you are measuring here, V terminal open circuit, will equal directly to EA. Okay, guys? And you keep changing this DC voltage, so the current I field changes. And by changing the field, because you know this, EA equals K phi omega M. So we do not change omega M, it equals omega S, the synchronous speed, constant all the time here. So that means any change in the flux will be directly translated into change in the induced voltage, yeah? And the induced voltage will equal the terminal open circuit voltage here. Okay, guys? So you keep doing this and you just plot those together. The terminal voltage open circuit, that's the thing you can measure, but you know it equals the induced voltage inside the machine with IF. So while IF is small enough, like this here, so the increase will be linear. So this relationship will be linear here, okay? That is the linear region. But with keeping increasing I field, you will start decaying and going into saturation. This we call the saturation region. I explained this before when I talked about DC machine because it's the same principle. You having the field winding like this. So I have a coil on an iron core. So this is an iron core. And I field is just going there. So if I field is small enough in this area in the linear region, if you increase the field, the induced voltage will just increase because the flux density will be increasing in linear fashion, okay? But if you keep increasing and increasing, that means more and more flux lines moving through this iron core, so there is no space for more. And that means the increase in the field current will not be translated into an equal increase in the flux density. That's why we call with the high value for I field, it starts decaying like this. So it's not linear anymore. So this is linear relationship, but this one is not linear. Okay, guys? So this we call the open circuit characteristics. Okay, guys? But does this give us XS? We came here to find XS, not to find the open circuit characteristics. But I told you to find XS, we need to do 2 tests, not just one. So this is the first test, the open circuit test. Now we go to find the third test, which is the short circuit test. Okay, guys? But still, this open circuit characteristics is very good. Remember, it is the same thing we found in our DC machine examples, both in the tutorials and the assignments. It is all the time, it is your way to find EA actually, because you cannot measure EA directly because that's something internally in the machine. You cannot just measure it with a voltmeter. So that is the way to find it, by plotting a relationship between it and the field current. Okay, and that's easy for now. If you know the field current you're talking about, you can just come to this characteristics and just go to the curve and find the corresponding induced voltage, EA. That is the only way, or the only obvious way you can use it to find the induced voltage inside the machine. But we came here to find XS. So we will proceed to the third test, which is the short circuit test. Okay, guys. Yeah, I just forgot something. So before proceeding to the short circuit test, just let me make sure you have something in mind. Sorry. So yeah, in a machine in a lab, we can have all the terminals of all the three phases outside, so we can deal with them. But in a machine in the real power system, typically, okay, so most of the machines you can deal with in the power systems, so typically the generators, armature terminals are internally connected in Y or delta connection. Okay, so yeah, like I said, it is just, so like I'm seeing here, we're trying to measure the voltage of this, and this is just per phase voltage, a single phase voltage. Okay, but sometimes you do not have the 6 terminals of the 3 phases, because they should be having each phase, each coil has 2 terminals, or you're just having all the terminals out. But if you don't have this, and the machine internally connected like a star or delta, Y or delta, and you have the connections outside, you have to make sure what you're doing, because you cannot measure the voltage of a single phase directly, rather you will just measuring a line-to-line voltage, because that is the thing that you have outside the machine. Okay, guys, so if you have something like that, you have to make sure you remember what it is. So if it is a Y connected, that means the terminal voltage that measured, which is a line-to-line. So if you need to find the terminal voltage open circuit, which we need in our circuit, which is the phase 1, so make sure to divide it by square root of 3. Okay, but it's a delta connection, you know, in the delta, so the measured will be the line to line, but in delta it equals the phase value. Okay, so if your machine is internally connected like a line to line voltage like this, you cannot directly apply something like this, so you have to make sure to do this. But again, in the lab and most of the laboratory connections, you should be having all the 6 connections out, so you can deal directly with just one phase. Okay, guys, so that was the open circuit test, and now we can go to the short circuit test, the third test to do here. For this test, we continue to testing the machine also in a lab setting. So the 3 tests should be performed in order. So we start with DC test, and then open circuit test, and then jump to the short circuit test. Okay, that's why the first step in the short circuit test will be to restore the field voltage back to 0. Okay, so make sure you just restore the voltage of the machine of the field winding back to 0. Okay, before performing the test. That's out of safety. Okay, so you don't need to apply a high amount of voltage to the field winding. That means you have a high amount of field starting this test, especially the short circuit test, like we are when we'll be seeing now what will happen in this kind of a test. That's why we have to do this test with extra precaution. Okay, so number 2 will be short circuit the armature terminals. Okay, that's why it's called short circuit test. That means you place a short circuit on the all terminals of the machines. Okay, so there's a Y connected. That means they have 3 connections together, so the other 3 connections you just short circuit them together. Okay, if it's a delta connection, it will be 3 connections out, so you just short circuit them together. That's what I'm saying. So you place a short circuit on the armature terminal of the machine. Okay, as a power system engineers, we don't like the term short circuit because it's all the time linked in our mind with a problem, a catastrophe. So we are placing a short circuit in purpose here because that's how the test is run and how we can find out what we need to find in the machine. But we have in mind that it is some sort of a dangerous situation. We are now experiencing the winding. So the winding is short circuited. That means any excitation the machine will have will be just translated into a very high current moving through the winding. So we have to do this test with extra cautious. Okay. So after short circuiting the machine, we again drive the rotor using the external mechanical torque coming from the motor in the lab, okay, until it reaches synchronous speed again. Okay, it's also because that is the normal operating conditions of the machine, the synchronous speed on 120 F/P. Okay, guys. Number 4, and here's come the dangerous part. Very slowly increase the field current until the armature current reaches its rated value. Okay, so we slowly increase the field current until the armature current reaches the rated value. What do we mean by the rated value? So the rated value is the value which the machine is designed to work at continuously, okay, without damage. Okay, so it's important to say it's continuous work. So this is the value, so whatever it is, the rated current, the rated voltage, whatever the rated speed, the rated torque. So these are the values of the machine designed to work at all the time, and it can be working at all these values all the time without being damaged. Okay, that means that I'm saying continuously, okay, because the machine can handle a little bit higher than those values, than the rated values, but for a very short amount of time. But it's not advised, it's not something we like. So the typical working condition of the machine to be working at the rated conditions all the time, the rated voltage, rated current, rated torque, and all that stuff. That's why I'm saying increase the field voltage, the field current, and the field voltage until the armature current reaches its rated value, and stop increasing because you're now dangerousing the machine. The armature winding, if exceeds the rated current for a considerably just amount of time, the winding may be burned down. Okay, and that's why we have to do this step with a very high cautious. Okay, guys, and the whole point is because because the armature terminals are shorted, okay, just a small amount of IF will reach the armature current to its rated value. Okay, that's why I'm saying you don't need to give very high current. It's a very small amount of current of I field will bring your armature current to its rated value. That's why, because it's short circuited, guys. So that's why I'm saying that is a dangerous test. Do it with a very high amount of cautious. Okay, so again, why are we doing this? Back to the equivalent circuit, JXS RA, and here is the induced voltage EA, and now that is V terminal. In the test, we are just placing a short circuit here. Okay, guys, that means the current moving here is IA, and we are placing an ammeter just here to measure this current. Okay, guys, and that is the field circuit. That is a variable V field on VDC. Okay, and that is the I field, and here we place another ammeter to measure IF. We gradually change this voltage, so I field will be changing gradually also, and this will cause IA to be changing also. Okay, guys, so plot those together, IF and IA. That is IF and that is IA short circuit. Okay, now it will be a linear relationship, because I said no saturation are talking about here, because it is just a small amount of I field will bring your IA to the rated value. Okay, that is we would call the short circuit characteristics, as the relationship between the armature current and the field current while the armature terminals are short circuited. Okay, guys, so we have the open circuit test that gave us the open circuit characteristics, and have the short circuit test giving us the short circuit characteristics, and how to find XS from those guys. And that's the question. So for the short circuit state here, you know, from the equivalent circuit, this equivalent circuit here, that is JXS, that is RA, that is EA, and the terminal voltage here just short circuited, and that is IA. So from this equivalent circuit here, you will find this EA equals IA short circuit multiplied by RA plus JXS. Okay, guys, as for our information for a typical synchronous machine, XS is just so much higher than RA. That means you can sometimes neglect RA without a big impact on the results. That means if you just remove this RA from this calculation here, this will mean XS will equal, almost equal, because we're just neglecting RA, so it's almost equal EA divided by IA short circuit. So that's how we can find XS. So IA short circuit, you can measure it, okay? But how to find EA? They're the same problem again. How to find EA? That's something you cannot measure. And that's why we need the open circuit characteristics. So to do this, we need both the open circuit and short circuit characteristics. Okay, guys, here. That is I field, and you place both of them. So that is the linear region for the open circuit characteristics. That's a linear region here, and after this you're entering the saturation region like this. So that is EA open circuit. Okay, and on the same axis you just plot IA, so that is IA short circuit. So I'm placing both of the characteristics on the same curve, and now that's easy. You can just find at any amount of IF here and just go with a vertical line like this. It will give you two values, E open circuit from this curve and I short circuit from this curve, and that's how you find XS. It will be EA open circuit divided by IA short circuit, because now we are just dealing at the same amount of field current. Okay, so that is the whole point of this. To find XS, you just need to divide EA by IA short circuit. Okay, but you don't know how much EA is now moving inside the machine. So you go at the same amount of I field and find both of them, EA and IA, because that is EA that is corresponding to the same field current applied at this value you want for IA. Okay, guys? By the way, that means here you can just find any point. So IF can be any point on this axis, but you'll have a little bit of a difference here. Before, so and here, so let me remind you that we call the linear region, and that's called the saturated region. Okay, so it is in the linear region here, that is XS. Whatever you divide EA by IA, there should be a constant value for XS. That is why you call it XS unsaturated. Okay, because that's in the linear region, in the unsaturated region. Both of the characteristics, the open circuit and short circuit characteristics, both of them are linear, so dividing them together will keep you almost constant all the time. But if you just go high enough to the saturated region, now IA keeps to be linear like this, but the open circuit characteristic E starts decaying a little bit. That's why XS starts decaying like this. So XS will now start going down. And that's why we call it in this region XS saturated. Okay? So if you want the unsaturated value for XS, pick a value from this where IF is as small as possible. That's guaranteed you are working in the linear region, and that will give you the value for the unsaturated XS. Okay? And that is actually the value we deal with most of the time. But if you're working in saturated region, now it will be different from IF to IF. So that means you need to find a specific value for IF and find IA and EA and just work at them. Okay, guys? So that means just if you find XS, this XS, unsaturated, for a current value IF here, that means if you want XS at another value IF here, you don't need to recalculate it. It should be the same. But if it is at the high value of IF here, maybe, that in the saturated region, no, you have to calculate it again, because at this value, you are entering the saturated region and XS starting to change, not rather than to being constant in the linear region. Okay, guys? So keep that in mind, that we call XS unsaturated and that is XS saturated. Okay, guys? Okay, so what we did today at the wrap up here is we performed the testing of the synchronous generator. So you have three tests: the DC test, short circuit test, and open circuit test. DC test is used to find the armature resistance, RA, and open circuit test and short circuit test used to find the open circuit characteristics and short circuit characteristics, which can be used to find XS. Okay, and also can be used directly. There's the open circuit characteristics, maybe will be used all the time to find the relationship between IF and E, like we did before with the DC machine. Well, we just didn't have a mean to just access EA, which is something inside the machine, rather than having this relationship and use it. So we just know the amount of field current you are dealing with now and just enter these characteristics to find the corresponding E. Now we have EA and XS, so you can use the very first equivalent circuit like this to predict the performance of the machine, whatever it is. Okay, so next time we'll be proceeding like we did with DC machine. We will just discuss the power chart, the different power and power losses inside the machine, and we will be just jumping into study the performance of this machine with different operating conditions. Okay, guys, so the next tutorial we should be just solving problems and worked examples over these principles, just to make these principles solid, and try to solve any problems that jump into your mind about this before going into more engineering wise explanation for the synchronous generator. Okay, thanks so much guys for joining me today, and I hope to see you next time.